Okay, Physical Organic Chemistry, ch7.3.1-7.3.2. Today we're going to cover section 7.3 in your text. We will cover each of these subsections, 1, 2, 3, 4, 5. They may be in more than one video because we want to manage the timing of these. Okay, these are some of the most critical conceptual issues that we need to understand in terms of understanding organic reaction mechanisms, and so our discussion today will focus on the conceptual. 7.4 will take us into the quantitative when we do kinetics. All right, let's start with the Hammond postulate. This is figure 7.7 from your textbook on page 375. Again, to remind you, this is our reaction coordinate diagram, the progress of the reaction along the x-axis, potential energy along the y. We have a reactant A going to a product B. These are, in this case, an exothermic reaction. Most reactions are exothermic, but they don't have to be. Of course, then we can determine the height of the barrier for this, indicated by C, and then what you notice is that the transition state, which occurs at height C and indicated by point D here, is closest to the reactant or product for which its energy is nearest. So in this case, transition state D is nearest in energy to A, and we would then infer that its structure is also most like A. This is the Hammond postulate. Now this has other manifestations. So these are 3D Morel plots here in figure 7.8 that illustrate the Hammond postulate. Let's start actually with B, where our reactant and product are at almost the same energy. So what we see here is that the transition state is approximately halfway in between the reactant and the product in this instance. In contrast, for a reaction that is exothermic, the transition state will be closest in energy to the reactant, always for an exothermic reaction, and so it will most resemble the starting material. In an exothermic process, and we see this many times with intermediates. Here we're talking about a reactant and a product, but of course an intermediate in a single microscopic step, the intermediate is the product. Here we see that of course the product is higher in energy because it's endothermic, and the transition state is closest in energy, and we would infer closest in structure to the product of that reaction. All right, so one of the manifestations of the Hammond postulate is that as we lower the energy to get to product, that the transition state shifts from in an endothermic step, being closest in energy and closest in structure to that product of the endothermic step, the transition state shifts systematically to the left and becomes closer to the reactant. Now there's a place where the Hammond postulate has already given us great insight, and that place is in the formation of carbocations. If you recall, we said that the tertiary carbocation was much more stable than a secondary carbocation, which was more stable than a primary carbocation, and much more stable than a methyl carbocation. And this is manifest in SN1 reaction rates that we see many times. So again, with the Hammond postulate, we see that as we stabilize the carbocation, the energy of that transition state also comes down, as we saw illustrated in the generic or theoretical form in the previous slide. Now this is from the insight in your textbook on page 377. I encourage you to read that and understand it in detail. Okay, so in those illustrations, the Hammond postulate gives a very direct correlation. Now, in this case, the correlation isn't as direct, but it still obeys the Hammond postulate. If you look, The endothermic step, the transition state, is closest in energy to the product. And in the exothermic reactions, the transition state is closest in energy to the starting materials. And so these are good. They give us insight into how to think about the transition states, and those insights will often help us design, improve reactions and selectivities. So speaking of those, there's an aspect of this that's very practical. We'd seen this already. Okay, there we go. This is now section 7.3.2, considering selective versus reactive species. And we'd seen this in halogenation. So let's consider a simple system. We have tertiary and primary hydrogens in this system. Okay. This can react with the halogen radical, either the chlorine or the bromine, and we can get two products. The product of substitution at the tertiary position and the product of substitution at the primary position. Now that's considering only monosubstituted products, and that's a whole nother beast, but let's just focus on this for now. Now, you need to recall some information. First, in terms of tertiary versus secondary versus primary reactivity, for the chlorine, we see a ratio of 6 to 4 to 1 in the selectivity. But for bromine, we see a ratio of 19,000 to 200 to 1. And of course, we have said before, the bromine is selective. We can very selectively form the tertiary bromine systems, but chlorine is reactive, and we get to often terrible mixtures of products. Now, how do we understand and explain this? Well, the other product that's formed here is HX, and it is the thermodynamics of that bond that drive this. For HCl, that BDE, is 431 kilojoules per mole, whereas for HBr, it's 366 kilojoules per mole. Now, this large difference let's see, what is that equal to? About 65 kilojoules per mole. Okay. And of course, there are about 4.2 kilojoules per kilocalorie. So this is about 15 kcals per mole difference. And this large thermodynamic driving force for the formation of HCl means that it reacts so much faster at any of those positions, and so there's a very small difference in the transition state energies because it's so thermodynamically downhill.